everyone, welcome to the last lecture on orbital mechanics. So this is the lecture 5, which is the last lecture under the unit orbital mechanics. So in the last lecture we are going to see about the estimation of orbital velocities and the escape velocities. So we will see what is orbital velocity, we will see what is escape velocity. We will see the orbital velocity with respect to the two-body system and the three-body system or three-body problem, and finally the escape velocity for the same two-body problem and three-body problem. With that will conclude this unit. Okay. Now, when it comes to the case of orbital velocity, orbital velocity, we start with the concept of centripetal force. Like here, in order to derive the orbital velocity, we have to start with the centripetal force and the gravitational force. So first let me say what is orbital velocity. Orbital velocity is the velocity required by the satellite which is actually revolving around certain planet, okay, in order to stay in that orbit, okay, it has to, in order to stay within that orbit, okay, that is nothing but the orbital velocity. Let us try to derive the formula for orbital velocity. In order to derive the formula for orbital velocity, we have to start with the concept of centripetal force and the gravitational force. The centripetal force is nothing but the centripetal force is nothing but kinetic energy. Okay, centrifugal force keeps the object moving in a circle, and the gravitational force between the object and the celestial body provides the necessary centripetal force for the circular motion. So only the gravitational force provides the necessary centripetal force for the circular motion. So the centripetal force in a circular motion is actually represented by mv square by r, where m is nothing but mass of an orbiting object, v is velocity of the object, r is the distance from the center of the celestial body to the position of object orbiting position. Okay, now, so we know this gravitational force should be equal to the centripetal force. So under that condition, we know what is gravitational force. So gravitational force is given by F is equal to g m1 m divided by r square, where m1 is mass of the primary object, m is the mass of the satellite or the secondary object. Okay, g is gravitational constant, r is the distance of separation between them. Okay, by equating the centripetal and the gravitational force, because the gravitational force is supposed to provide the centripetal force that will make the system to orbit around the primary. Okay, so and so we are comparing this centripetal force with the gravitational force, which is nothing but mv square by r is equal to g m1 into m divided by r square. So when I solve, I will get the final expression as v is equal to root of g into m1 divided by r. Okay, root of, everything comes under the root. This entire thing comes under the root. Square root of g into m1 divided by r. Okay, so this formula for orbital velocity Vr is Vr of an object orbiting around a celestial body with a mass m1 at distance r from the center of the celestial body. So the g is nothing but the gravitational constant. It is important to note that the derivation assumes that the orbiting object is much smaller than the celestial body. Actually, it is much smaller than the celestial body. Obviously, if you compare a satellite in size of the Earth, it's going to be very small, or if you compare the satellite to any celestial body of observation, size is going to be very less. Satellite size is going to be very small. The test object size is going to be very small. Okay. Additionally, the derivation is based on the circular orbits. So in reality, celestial bodies often have elliptical paths, and the gravitational force varies with distance. However, for small orbits around the larger celestial bodies, the circular approximation is generally accurate. Now, when we find, this is okay, same slide has been repeated. Okay. Now, when we consider the same orbital velocity in case of a three-body system, again when it goes to the case of three-body system, that was with respect to two-body system. Okay, when we take the three-body approximation, three-body problem, under that case the Vr depends on g into m1 plus m2 divided by r. So the formula reveals that velocity depends on combined mass of celestial body m1 plus m2 at the distance r from the center. So r is nothing but this is r from the center. This center is nothing but barycenter, okay, from the center. For example, to keep the satellite in a stable orbit around the Earth, one must calculate the orbital velocity based on Earth's mass and the satellite altitude r. We have to measure in such a way, and then we have to put it into the orbit. Okay. This is about the orbital velocity. Then there is another thing called escape velocity. So what is this escape velocity? So once we are launching a satellite, it has to initially cross the gravitational boundary of the Earth, and then it has to go to the space and set into the orbit and revolves around that primary object or the Earth in that orbit in the orbital velocity. So then what is this escape velocity is that the velocity required by the satellite to leave the gravitational field of the Earth is called as the escape velocity. Here we consider object of mass m, which is at distance r from the center of the celestial body with mass m1. We calculate the minimum speed required, not maximum speed, the minimum speed required for the object to escape the gravitational influence of the celestial body. Okay, that is calculated. So gravitational potential energy is given by, it is not gravitational force, it is gravitational potential energy, which is nothing but into r, f into r. So that we will get as u is equal to minus g m1 m divided by r. Okay, it is not r square, it is, since it is energy, it is divided by r. So g is the gravitational constant and m1 is mass of a celestial body, on Earth m is the mass of the test object or the satellite. Okay, r is the distance from the center of the celestial body to the object's initial position. The negative sign in the equation indicates gravitational potential energy decreases as the object moves farther away from the celestial body. The next is escape velocity. So that initially what we have seen is nothing but the potential energy. So potential energy is due to the gravitation. Then next is the kinetic energy. Kinetic energy is nothing but half mv square. So the total mechanical energy is the sum of E is equal to potential energy into kinetic energy. So that is nothing but 0.5 half mv square minus since even though this is plus, the sign in the potential energy is minus, okay, because it decreases as it moves far away. So minus g m1 m divided by r. Okay, when I solve this, I'll get escape velocity as, I'll get the escape velocity value as. Okay, so sorry, this is the escape velocity E, total energy. So this is the total energy, mechanical energy for the system. Whatever system is there, the total mechanical energy of the system of mass, total mechanical energy. Now we are supposed to know how much mechanical energy. This is the total mechanical energy needed by the system in order to go to the in order to reach the gravity, or this is total mechanical energy, and this energy should be greater than 0. This energy should be greater than 0 because this is potential energy provided by, okay, this is the potential energy provided by the Earth itself. This is the potential energy provided by the gravitation. Okay, this is the kinetic energy of the object. So total mechanical energy of the object is this. So this is due to gravity and this is due to the applied velocity to the body. Now, in order to make the object to leave the gravitational effect, obviously either this two terms has to be equal or the first term should be greater than the second term, right? So that is the condition we are going to apply. The difference should be greater than or equal to 0, which means the escape condition is that the total mechanical energy should be greater than or equal to 0. So solving for escape velocity, when I equate it to 0, then that is the minimum energy required to escape from the orbit. So that is the escape velocity. The minimum velocity required to leave the gravitational influence of a celestial body is calculated by equating the total energy to 0. So when I equate it and find the solution, the V escape is equal to the root of 2 into g into m1 divided by r. It can be seen that in a two-body problem, escape velocity is required for mass of m to break the gravitational influence of celestial body, which is at a celestial body of mass m1 at distance r from its center, is v escape. Okay, this escape velocity is independent of, it is very important, this is independent of the mass of the object in case of a two bodies problem. In case of a two body problem, it is independent of the mass of a escaping object, whether it is a satellite, spacecraft, or even a tiny pebble whatsoever it is, even from a tiny pebble to a satellite whatsoever may be the mass of it needs, okay, they all need the same escape velocity to break free from the celestial body's gravitational pull and continue their journey to the space. Okay, this concept is a fundamental in this concept is fundamental in space missions, interplanetary travel, and understanding the dynamics of the celestial bodies. Okay, now this is the case when it is of when the problem is a two body problem. But now let us consider a three body problem. When we come to the case of a three body problem, it is never going to be this simple. Okay, the case is different. So how it is different? Here the formula for calculating the escape velocity, same, is E is equal to first the total mechanical energy of the system is given by, this is the kinetic energy, whereas the potential energy of the system includes the mass of that system also. Okay, here the mass will not cancel out in the later part, we will see that. So that is nothing but mass gravitational effect of the first system plus gravitational effect of the second system. Gm1 into m divided by r1 plus Gm2 into m divided by r2. Okay, so g has been taken out as common, so we have this expression. So v is the velocity of the test mass, m is the mass of the test mass, g is the gravitational constant, m1 m2 are the masses of two primary bodies, r1 r2 are the distance from the test mass to the center of m1 and m2 respectively. Okay, now the same condition applies. The total mechanical energy should be greater than or equal to 0 when I want to solve for the minimum energy required to escape the gravitational influence of the celestial body is obtained by equating the above expression to 0. When I equate it to 0, I have escape velocity equation as this. Okay, so 2 into g into, it is not just m1 by r, it is m1 m divided by r1 plus m2 m divided by r2. So the escape velocity in the three body depends on mass of all the three bodies. It is also depends on the test mass. That is very important in case of the three body problem. That is not the case in case of orbital velocity, but in case of escape velocity, the mass of the object is under consideration when we go for the three body problem. Okay, there are relative distance r1 r2 from the test mass, and the escape velocity can vary significantly based on the specific configuration of the three body system. It is essential to note that the restricted three body problem, some regions are known as Lagrange points, have special properties where the effective gravitational fields from two bodies balances the centrifugal force of the test mass, allowing them to remain stable in the position related to the two larger masses. These points are crucial in the space missions and satellite placement. Escape velocity can still be calculated and for the test mass outside these stable points, and it will be influenced by the gravitational interaction of all the three bodies. Okay, this is all about the escape velocity. So in summary of this, we have seen about the orbital velocity, the two body and three body system. Both orbital velocity has been discussed. In case of escape velocity, the two body system, the escape velocity is independent of the test mass or the smaller mass, which is under the influence of large two celestial bodies, whereas in three body system, it depends on the escape velocity, depends on the test mass. Okay, now we will come to the overall conclusion of the orbital mechanics. In case of the orbital mechanics, in the first unit we saw a very minimal outline about the description of the solar system. In the second lecture we have seen about Newton's law of universal gravitation and Kepler's law of motion. In the third class, we have seen about two body problem, where we have derived the equation of motion and the total energy at any point for a test object or test mass. Okay, that we have derived. In the two body system, we have even proved all the Kepler's law, which has been along the equation that has been proved. And in the fourth class, we have seen about three body problem. The three body problem, in this three body problem, we have considered that two bodies are of larger size and they are a circular motion about the barycenter. That is a consideration. And the third mass test object is of very small size compared to this. Under this consideration, it is considered as a restricted three-body problem. So for that three-body problem, we have just seen that the total energy depends on the kinetic potential energy and the kinetic energy. The potential energy is effective potential energy that takes into account the centrifugal forces also. So that is why it is called as centripetal forces also. So that is why it is called as effective potential energy plus the kinetic energy. Okay, so centripetal force plus gravitational force together forms the potential energy, and this forms the and it has a kinetic energy. From that, as a next point, what we have done is that we have seen the Jacobi's integral, which is the Jacobi's integral actually works on the conservative energy conservative systems where the energy is conserved. So total energy at any point is going to be constant. That is what Jacobi integral indicates. So from the Jacobi integral, then we go for the next points called as the liberation points. So liberation points are actually derived using the Jacobi integrals, but that is not the scope of the subject. But let us know what is the liberation points. Liberation points, according to the three body problem, there are 5 liberation points. L1, L2 and L3 are the liberation points which are unstable. L3 is completely unstable, where we will not keep any objects, whereas L1 and L2 are marginally stable. If there is any atmospheric drag that is causing the satellite to shift or drift from the orbit, then it is not a stable point, and otherwise it is a stable point. So we can in general say L1 and L2 and L3 are unstable points, whereas L4 and L5 are very stable, and because even if there is a drift from the orbital positions at L4 and L5, the orbit oscillates but return back to the original path in case of L4 and L5 points. Okay, that is stable point. So last topic which we have covered is nothing but the orbital velocities and the escape velocities. So we have seen the orbital velocity and escape velocity for both two body problem and the three body problem. So with this, we are winding up the lecture series on orbital mechanics. So if you have any doubt, please feel free to mail to the mail ID professordeepthi@gmail.com. Thank you.